Okay, so a part of what I'm doing for background research is to just check in and see what other folks have been doing with respect to zero knowledge and the process calculator. And I remembered this paper from 2008, in which Michael Bacchus, Matteo Maffei, and Dominique Unruh developed an applied pi implementation of zero knowledge, and used it to analyze the DAA protocol in trusted platform modules. So this is the direct anonymous attestation protocol. So in case people don't know, so I just wanted to take a look at what they've done, and I'd forgotten, it's quite an interesting approach. In case people don't know what applied pi is, it's kind of in some ways you can see it as halfway between pi calculus and row calculus. So that it's used almost entirely in a static analysis context as opposed to an execution context. And the reason is because applied pi is more of a framework. So you have pi calculus to which you add a Levere theory of your choosing. So it's like if you had pi calculus wedded into K framework, something like that. So K framework allows you to spec out a Levere theory or something very close to that. So this is where you've got a pi calculus, and what you're going to send and receive are things that are in a Levere theory. So I'll show you that in a minute. But then what's unique about what their approach is that they give a Levere theory for a general accounting of zero knowledge. I mean, it's still just a flavor of zero knowledge. It's not all zero knowledge protocols, but it does capture a broad range of ZK stuff. And then they were able to find an attack that they analyzed the DAA protocol, and were actually able to find an attack that the original proof of correctness had not found. So how did they do that analysis? Well, the analysis was done entirely automatically because there's a tool called ProVerif, which allows you to do static analysis. So you specify, you add to ProVerif your Levere theory, and then you can write down protocol specs, and then it will do analysis, essentially resolution style theorem proving, and essentially check to see if you have your protocol can be proven to be correct. So having done that, they found an attack to DAA automatically, and then proposed a variant which is automatically proven correct. So before I dive into some of the details, I just want to stop here and check and see if overall that makes sense.
Yes.
Yeah,
sounds good.
makes sense.
Okay, cool. So the key trick with the applied pi calculus, as I said before, hang on, let's get this thing expanded a little bit. Here's the basic spec. So this is down if we focus down here first, this is sort of your usual pi extended with some syntactic sugar in terms of an if then else. So this is very much like the row match, right? You can implement if then else using match and vice versa. And now input is the same. So this would be our for comprehension. So input is the same. You've got a variable on a channel. Output is different. So output is drawn from something up here. So they use these variables here to range over these sorts of things here. So these are called terms. Terms are either names or they're variables, or you've got some function symbols applied to terms. So if the arity of f is k, then you would have k terms here. So this is, pretty much a Levere theory. Any questions about that?
So this f as a function is so all of this is all terms are like channels, right? Something like channels.
No, these are going to be like messages. These are structured messages.
Oh, I see. So
right?
So we are not sending processes. We are sending these terms.
You're only sending terms. Yeah.
Oh, okay.
Yeah, that's what I'm saying. It's kind of halfway between pi and rho. They don't do the loop.
Oh, I see.
Yeah. Then the COM rule is pretty much as we expected. It's a synchronous output, right? So if you have an output meeting an input, it's very interesting to see. There's just this little detail to see the difference between the way the COM rule is stated for someone who thinks of pi as a generalization of lambda and someone who doesn't. So if you think, like Milner thinks of pi as a generalization of lambda. So in lambda, you always apply a function. This is the closest thing to a function, to some data. So he always puts this over here and this over here so that it's most like lambda. Does that make sense?
Yeah.
So these people are not seeing the connection between pi as a generalization of lambda. Of course, par is commutative, but it really reveals the presentation of the COM rule, whatever it is, reveals something about the way people are thinking about these things. Anyway, so this is synchronous in the sense that you've got a continuation for output, right? So this is not an asynchronous calculus. Just note that. So, they match on the channels, the input and output match. And so then you would move forward. Interestingly, they don't do substitution here. So that's something, yeah, they do the substitution here. This is a mistake. This needs to be an n, and this needs to be p with n for x. They say it down here, but they don't put it here. They should have done. So if you have true in your if then else, then an if then else in the test of the if then else, then it moves to p. If the environment in which you're running does not validate that m is equal to n, where these are terms. And they're ground terms, right? There are no variables in them. Then the if then else evolves to the else clause, the Q. Any questions about that?
You said that in the COM rule, the X will be
and the output, this should be an in. This is not even syntax. Well, it is syntactically well formed, but they mean something else. They say it down here in English.
Okay.
Yeah.
And a question between relation between synchronous and asynchronous. If we say that P is nil or stop process, can this be like equal to asynchronous version?
Yeah. If the only thing you could put here is a 0, then it becomes asynchronous. But because you can, yeah. So P is hanging out, until the communication happens. So if you restricted it to 0, then you would get your asynchronous.
And there is no replacement or substitution inside P.
There is.
P is. Oh, there is. Okay.
No, I'm sorry, not in P, in Q. Sorry, in Q.
Okay.
Not in P.
Not in P. Okay.
Yeah, exactly. And then of course they have replication as well. So that's another difference between row. But you can easily see how you could add Levere theories to row, right? That's a very straightforward thing to do. Anyway, so that's the basic idea. Again, one of the points I like to make about the process calculi in general is how flexible they are, right? So to go from pi to applied pi, I mean, look at what the changes are, right? It's still half a page, right? So super powerful mathematical framework. We can add Levere theories and get something that's very useful. So now on to the zero knowledge stuff, which is very specific. So it's divided into 2 bits. All right. So the first bit is sort of some base cryptographic primitives. So they have pairing, they have symmetric and asymmetric encryption. So pairing is exactly as you expect, right? So the first of pair XY is X, the second of pair XY is Y. If you encrypt X with Y using Y, so Y is the encryption mechanism, X is the message. So if you decrypt the thing you encrypted with Y, then you'll get back X. Now here you have a private key and a public key and a secret key. So if you encrypt with the public key, and if you encrypt X with the public key part of Y, and then you decrypt that with the secret key part of Y, you'll get back X. Does that make sense?
Yeah.
And so the rest of these are pretty much as you would expect. All right. So over here, it's a little bit, hopefully what I gave you was the key to being able to read this. That's the idea. Over here, it's a little bit more interesting, right? So this is what they are calling, the zero knowledge part. So you add to this Levere theory some additional stuff. So to understand it, it's easier to go into the equations, but overall, what you've got is an infinite set. So that's important. The equational theory presented this way is an infinite set, and then they reduce the infinite set down to a finite set that they can fit into ProVerif. Now I'm still just getting up to speed on the whole thing, so you'll have to bear with me a little bit. But you have formulae of the type zero knowledge ij, and this is going to be of arity I plus j plus 1. So if you look down here, you can kind of get a sense of that. So you have I m's, j n's, and one formula f. And f is an of arity 0. So this is some kind of constant, right? So it's a formula that is representing some zero knowledge property. So you have sorry, formulas of arity 1. My mistake. Alpha I and beta I and true are of arity 0. So these are the constants. Formula is of arity 1. So if you so formula is going to take something like likewise a public is also, I think, of arity 1. Yes, public and formula are of arity 1. So you have public sub p of, and then it's always going to be one of these zero knowledge formulae. And the P is going to pick out the pth n. And then the formula of this thing picks out the F, right? So these, you can think of these like accessors. Yeah.
Oh yeah. Mm-hmm.
And
I'm just
then
saying yes.
what's that?
I'm just saying yes.
Okay, cool. And then you have verifier ij, which is of arity 2, or verify ij. So what it does is it takes the formula in the first position and one of these zk assertions or terms in the second position. And it's going to be true if the environment for the zk validates that f with alpha for m, and sorry, m for alpha and n for beta is true. Right, did I get that right? I just double check that I've got, yeah, n for x, yeah. So the left hand, just, it's normal. Yeah, so you're putting in m for alpha and n for beta is true, and f is an ij formula. So they give a definition of an ij formula down here. So a term is an ij formula if the term contains neither names nor variables, right? So that makes it ground, and it's ground without names, right? So it's a ground term. There's no variables in it, and also there are no names. And if for every alpha k and beta l occurring therein, we have that the indexes fall within the I and J range, respectively. Does that make sense? So you've got some term, right? So it can, so our terms can be, formed out of this thing, sigma zk. Okay. So then these things are playing in the role of placeholders, right? So F, they're sort of being very careful about their placeholders. And yeah, so alpha and beta are giving you a special kind of variable set. Does that make sense?
I'm looking at so this F. I'm not completely clear what does it mean inside F to replace alpha with M and beta with N.
So what they're doing is uh, they're they're um, they're making it so that they have a divided namespace. So alpha is only ever going to be replaced by M's, and beta is only ever going to be replaced by N's, where the M's and the N's are come from a marker, a ZK marker. So this part is going to be, let me make sure I get this right. Yeah. This is the private part, and this is the public part. Okay. So this is stuff that is known to the outside world. And this is stuff that's only known to the verifier, I think. Yeah, right. So this stuff is known by adversary, and this stuff is known all by adversary and verifier, and this stuff is known only by verifier. Okay, does that make sense?
Okay. Okay.
All right. All right. And so the alphas and the betas are making sure that you only ever put public stuff in public slots and private stuff in private slots.
Okay.
So alphas are private, betas are public. So namespace technology to the rescue yet again. Does that make sense?
Yeah. Yeah.
Okay. So here's an example. So notice that here's so ZK has private part, public part, and a formula. Here's a ZK. Private part is the key. Public part. Oh, and they introduced these. So notice here that we have IJs, and the IJs are used to give you the run length of these vectors here. You can get rid of the vectors if you put semicolons here to mark, okay, I've come to the end. So I've come to the end of this vector and I'm moving on to the next vector. So that's what they do. That's what they do here when they introduce the semicolon notation. So notice how here they've got commas, right? All right. So this part here is the key. This is the message. This is the symmetric encryption of the message with the key, right? And whenever they do this, this part is assumed under the symmetric part to be secret. So you don't get to see the key, you just see the encryption. You can't see the components, you only see the result. Does that make sense?
Yes.
Okay, and then the formula is that beta 2 is equal to encryption symmetric beta 1 alpha 1. And this denotes a zero knowledge proof. So this thing denotes a zero knowledge proof that the term encryption is an encryption of M with K. So this is denoting the proof of that. Okay. All right. So that's kind of the idea, and then they can implement a particular protocol. So at this point, I haven't really analyzed the protocol, but we can sort of analyze it together, and see what they've got. Here's the protocol. spec right here. So they've got a bunch of private channels, KA through KSN. So it looks like they've got an A process, a B process, um, and some server processes. Um, and then the protocol is the parallel composition of those. So what are A and B? Let's see. So here's the message, the ping pong diagram. They don't really say what A and B are doing. So party B, this one, receives a signed message from one of the servers. So the idea is that the signed message might serve as a certificate that allows B to prove that he has been authorized to contact A. Okay. And the point is that B wants to be able to convince A that he owns a signature on the message, but without saying to A which server issued the signature. Does that make sense?
Yes.
Okay. So then they should have parameterized. So this is really A of A, B. And it looks like test is going to mention Y somewhere. Yeah, so A is receiving on A some test, some value, and if the value passes the test, then it's going to output on B, okay, else bad A. B is receiving some value, and if you get a verification that the X is looks like the signing of a message AB with the private key KSI, then you send over to A zero knowledge of X. Else you say, hey, you sent me a bogus certificate. And then
so this is the checking when B receives the request from the server.
That's correct. That's exactly right.
And where is the key? Who owns the key? The B with his own key, or I mean, server is signing.
It looks like it's provided to the protocol. It's a parameter to the protocol, right? So this is some SKI. Yeah. So each server gets an SKI, and so the whole thing, all of these keys are in the scope of A, B, and S. Does that make sense? So it looks,
you say in scope.
That means that A, B, and S can all refer to all of these keys.
But they don't see the keys, right? Directly.
They do, right? There's a right. But notice that there's a private key part. So each one of these channels is bigger than just a. You can ask for a private key part and a public and public key part and a secret key part. So what these guys see is the channels, but they don't necessarily see the secret key part.
Okay.
Right, versus the public key part. Yeah, there you go. That's the trick. Okay. So yeah, and what it looks like is that the protocol outputs the public key part of each of these. Having done that, so there must be some environment in which is going to consume that. Having done that, then A is sitting there waiting for the Y, B is sitting there waiting for the X. and then each of these outputs sign pair AB with the secret key KSI, right? So each SI is going to use, right?
Yeah. And what this is received from SI is not really the signature directly, right? It's a ZK. So that A cannot check which server, on which public key this signature
That's right.
corresponds,
That's
right?
right. So what B is sitting on A is the ZK of X, not X. So it represents. Okay. So yeah. So what they're doing is they're abstracting away the specifics of the zero knowledge itself, and they just say, "I've got some zero knowledge apparatus." Yeah. So this is at a higher level than the level that I've been working, where I'm trying to I'm trying to identify the apparatus, and what they're doing is they're saying, I've got some kind of apparatus, and I'm going to formalize the API to that apparatus using this equational theory up here. Right? So this is the API to their apparatus. And that's actually very nice, right? This would give us good guidance as to how to put the API into Row. Does that make sense?
Yes, yes.
So this is a very good way to think about, like once we've figured out, exactly which ZK apparatus we want, packaging it up with using this as guidance is not a bad is not a bad idea, because as you can see, the protocols are relatively straightforward. It's very You could easily write this in Row, right? This is a for comprehension. Yeah. So this is lovely, right? I think this is a nice little piece, but what it doesn't tell us is the details of the ZK apparatus. So this is yeah. It would also be interesting to look at maybe porting a version of ProVerif over to Row. I think you could modify ProVerif to deal with the Row stuff. So that's another nice thing that we could. That's again, ProVerif is kind of halfway between. Yeah, it's not quite all the way to OSLF, right? But it's sort of on the way. It's generic in the Levere theory that you send as messages. So anyway, that's kind of what these guys did, and yeah, this is a good little uh, a good little chunk, which will, I think, help us understand how to organize the insertion of the zero knowledge apparatus as an API. Any other questions or comments from folks?
When you say API, you really mean something like special names inside the rolling, so that we can basically implement this protocol, right? We are sending it.
So no, I'm saying that this theory here gives us the right sort of functions. Yeah, you could say it as special channels, but in the same way that we have the list API in Row. This combo theory that's got the base, which is this encryption stuff, and this ZK stuff, that would be the kind of API that we want to expose in Row. Does that make sense?
Yes. Yes.
Cool. Yeah. So I think, and if we do that, if we were to do that, then we could potentially take a variant of ProVerif and use that to prove out the correctness of any ZK protocols that we implemented. So that's a nice halfway point to the full OSLF. So that's very interesting. Very interesting. Any other questions? Great. Well, I really appreciate the time. And I will see many of you in Dev Stand Up in about 22 minutes.
Yes. Thank you.
Thanks, Greg.
Sure. Ciao, ciao.
See you.
Thanks.
Bye-bye.
See ya.